The majority of people will at some time or other have gone on an elementary school field trip to an observatory or perhaps a science museum and have been told to stand around a huge weight that was suspended on a string and simply watch as it swings back and forth. The teacher would have said that if watched long enough it would seem to change course and swing in a direction that was different and was proof that Earth was rotating under the feet. Swinging pendulum experiment is proof that the Earth rotates. More often than not the focus of those watching would not be on the swinging pendulum or the fact that the Earth was rotating, but they would say that they could see it, even if they did not. However, as we get older, our thoughts may turn back to that swinging pendulum and wonder just how it could have been the proof of anything. Common sense would say that if the demonstration was in the building and the building was on Earth, if the Earth rotated then the pendulum would rotate with it. Foucault experiment I in 1851 was first of its kind. The experiment was first demonstrated in 1851 and is found in museums around the world today. It was Léon Foucault from France who suspended a weight of 61 pounds and dangled it from a wire of 200 feet in length at the Paris Pantheon and set it in motion. The bob had to be very heavy and the wire long enough in length to make sure that the pendulum was able to swing for a long time. Underneath the experiment, he put a pin on the weight's bottom and this drew a line, a circle of sand that was wet. After running for an hour the pin had drawn a line in the sand that intersected with the first line of the angle of about 11.25 degrees, which is just what Foucault had predicted would happen. This very quickly became a sensation on an international scale and it was an experiment that was to be repeated to the crowds in North America and Europe. Everyone learned that the Earth did rotate, but this had been the very first experiment that was able to measure the speed of it rotating. Due to the first experiment by Foucault, he received eternal fame and got a pendulum named after him. This would much later be the title of a book that bent minds, which were written by Umberto Eco and became a favorite in colleges. How playing catch at North Pole relates to Earth rotation, but just how did it all work? Well, to explain it some experimentation is needed. For instance, suppose a friend and you chose to play a game, and you played catch the ball at the North Pole. One person would stand on the side of the pole and throw the ball over the pole to another person, with that person standing opposite to you. Consider how it looks from the perspective of the ball. When it is released, it follows a path that is set by traveling in a line that is straight and going towards the person the ball was thrown to. However, it takes time for the ball to travel to the other person, and during this time the Earth has managed to rotate just a little. This means that the person who was catching the ball has now moved just slightly to the right. While the movement is only very slight, this means it would not affect the game much. However, if the game was played on a planet that had a rotation that was fast, then the person catching the ball would have moved more, and the chances are that the ball might miss that person and go past the left arm of the intending catcher. When going through its swing, the pendulum is acting in much the same way as the ball. When it gets to the top of the arc, the path is set and it is heading in the opposite end of the swing and will not deviate. This means that it will continue to swing backward and forwards on the exact plane. Now, if the pendulum had been suspended over the North Pole and a pin had been stuck onto the bottom and it was set swinging in motion, it would draw a line in the snow. However, in the time that it would take for it to reach one top of the arc and to the next, the Earth would have rotated. With each of the swings of the pendulum, the Earth would have rotated even more, and if the pendulum was to swing for 6 hours, or 1/4 of the day, the line it drew in the snow would intersect with the first line at 90 degrees. This experiment was actually undertaken by physicists at the South Pole in 2001. Anyone who has followed this up to now might say, but the pendulum of Foucault moved 11.25 degrees in 1 hour, which would mean that it would have changed 67.5 degrees in 6 hours instead of 90 degrees. If this is what you are now thinking, then you are correct, and it shows that the experiment done above would only work in the South or the North Pole. Pendulum experiment at equator. The same experiment could be undertaken at the equator. The pendulum would swing east to west. The Earth would rotate every time that the weight is in an arc. However, it would be moving in the same direction as the pendulum is moving. There is a lack of relative motion. The pendulum could be set to swing north to south and still the rotation of the Earth would not have any effect on the plane it is moving in. This is simply because the Earth is unable to twist under the setup and it always moves in the same direction. When it comes to the points that are in between the equator and the poles, more complicated geometry is needed to find out just how much the Earth is moving underneath the pendulum. In the period of one day, the plane the pendulum is swinging in would seem to change between 0 degrees and 360 degrees, like the equator and poles. An equation can be derived telling just how much the Earth had moved depending on the latitude. N equals 360 degrees sin, 0, with 0 being the latitude. If the pendulum were drawing lines, the angle of intersection between the first of the lines would be with one that was drawn some 24 hours later. In theory, anyone who got trapped in a room and who did not have a way out and who did not know where they were, and who had a piece of string and something to use as a weight, could find out the latitude.